after the gas laws, the basic gas laws, that is the Boyle's law, Charles law, Avogadro's law, and the consequence of it, the gas equation, ideal gas equation. Now we discuss other gas laws. These are applicative part, that is especially this Graham's law of diffusion. Graham's law of diffusion is next what we have to discuss. To discuss this Graham's law of diffusion, first we should know what is diffusion. What is diffusion of gas? Diffusion of a gas is nothing but basically the diffusion of a gas, very simple, is that transfer of gas. Transfer of gas from one place to another place. What is meaning here one place to another place? Here this one place is a region of, this is from a high pressure region to low pressure region. From a high pressure region to low pressure region. This is what is in simple meaning of diffusion. Suppose if you gas, you have certain pressure of 10 atmosphere, if you have certain amount of gas in a vessel, then that if you allow, if you open that vessel, or if you make certain outlet to that cylinder, then the external pressure is 1 atmosphere. Then you know that when the outlet is opened, so that means suppose you have a gas here which is at 10 atmospheric pressure, and this outlet if you open, then what happens, that this gas will escape out. Gas escapes out because the external pressure is 1 atmosphere, the internal pressure is 10 atmosphere. But here you know, when you open this, when the stopcock, when the cock is opened, gas from vessel escapes out, but not gas from outside, that is say air will not go inside the vessel. This will take place, but air inside will not go, because the pressure inside is high. So this gas will escape out, but air from the outer atmosphere will not enter into the vessel. So this is only one way movement, not the two way. So this escaping out of gas from, or transfer of gas from higher pressure to low pressure region is what is called diffusion. Diffusion of a gas. So here the gas is transferring from high pressure to low pressure. This is a very well known observation to all of us, right? And this is what we call diffusion. A more precise definition, this is according to practical observation. A more precise definition for diffusion can be given as that diffusion is a spontaneous intermixing of two or more number of gases. Spontaneous intermixing. Spontaneous means which takes place on its own, no need of intervening any other third agency or no need of giving any additional energy, nothing is required. Spontaneous intermixing, two gases are intermixing, means suppose here is a vessel and here is another vessel, right. The two gases, here this is gas 1, this is gas 2. If the both are allowed to pass into another large vessel, right, then here the pressure, obviously this two being the small vessels and this being a large vessel, here the pressure decreases. So, from high pressure region to low pressure region, both gases will come up, and here you will get a uniform mixture, and this will take place on its own. Spontaneous intermixing of two or more number of gases to form a uniform mixture is called diffusion. This is what is diffusion means. Spontaneous intermixing of two or more number of gases to form a uniform mixture. So, in the air we have a uniform mixture of oxygen and nitrogen. There, from different places, wherever high pressure or low pressure to balancing, that air will be keep moving, right. And this is what even our weather reports also sometimes will see the pressure at some particular stage and low pressure at Bay of Bengal, low pressure at some other, and the air will be keep moving in some northwest direction or southwest direction. All this is depending on the differences in the pressure, right. So, this is all is actually nothing but diffusion. Diffusion is nothing but spontaneous intermixing of two or more number of gases to form a uniform mixture. This is in simple what we will say about the diffusion. Then the next thing is, before discussing anything more about the diffusion, first we should know about the term rate of diffusion. What is rate of diffusion? Rate of diffusion is, you can define rate of diffusion in different ways as the number of moles of gas diffused in unit time, that is N by T, or volume of gas diffused in unit time, this is N by T, this is V by T, T is time, volume of gas diffused, or it also change in pressure in unit time, delta P by T, or it can also be defined as distance travelled by a gas in unit time, L by T. So, this rate of diffusion can be defined in different ways. The amount of gas diffused, the volume of gas diffused. When certain amount of gas is diffused, obviously there will be a decrease in pressure. Suppose if the gas is diffused from here to here, then there will be a decrease in pressure over here. So, that rate of decrease also will give us the rate of diffusion. So, the decrease in pressure in unit time, that also will give us the rate of diffusion, and what distance that the gas has travelled in a given time, whether it is travelled by 10 centimeters or whether it is travelled by 20 centimeters or whether it is travelled by 200 centimeters. This distance travelled also will give us because the rate of displacement is nothing but velocity. So, here the diffusion is also with respect to movement. So, it is nothing but velocity, right. So, rate of diffusion is nothing but velocity of gas. That velocity of a gas is nothing but what? So, rate of displacement, change in displacement with time. So, change in displacement, that is change in length, that is the distance travelled, that is nothing but displacement, that is L by T. So, in any of these ways that one can define the rate of diffusion. Now, in Graham's law what it was told is, the Graham's law is given, or Graham's law is given with respect to the rate of diffusion versus nature of the gas, means how the rate of diffusion changes with change in the nature of the gas, means whether all the gases will diffuse in same rate under the same conditions, or from one gas to another gas the rate of diffusion will it change with nature of the gas under identical conditions. It is something like, suppose if you have two different objects, one is very small and one is very big, either in size or in terms of mass, say 1 gram of mass and 10 grams of mass, say 1 gram of iron ball, 10 grams of iron ball, if both have been rolled under identical conditions with same velocity and all, then obviously the distance travelled by the small ball will be more than the bigger one, right, under all identical conditions. Then, so that means the velocity or the distance travelled displacement will be different for the two balls. So, that means it varies from one ball to the other ball depending on the size, mass, right, or density, whatever you take into consideration. Like that exactly, when you have two gases, and both the gases, if you allow them to diffuse under identical conditions of temperature and pressure, then obviously the gas with lower molecular weight, where the molecular size is small molecule will move fast than the bigger molecule. So, here one point what we can clearly understand is that the rate of diffusion not only depends on the external parameters like pressure, temperature and all, but also it depends on the size of the molecule, or density of the molecule, or its weight of the molecule. So, either way you can take it. So, this Graham's law actually gives us the relation between the rate of diffusion and density of the molecule. That what we discuss in this now, Graham's law, right. So, what the Graham's law says is, that the rate of diffusion of a gas is inversely proportional to square root of its density. Rate of diffusion is inversely proportional to square root of its density, means rate of diffusion, if I put it with the symbol R, then R is proportional to 1 by square root of 1 by d at, of course, the constant temperature. R is proportional to under root 1 by d. Rate of diffusion is inversely proportional to square root of density. So, when if it is inversely proportional to square root of density, also you can say that R is proportional to 1 by square root of molecular weight, because density is proportional to, density is equal to what? Weight by volume. So, density is proportional to weight. So, when rate is inversely proportional to square root of density, also it will be inversely proportional to square root of molecular weight. Also it is proportional to vapor density, right. Or also for two gases, for two different gases under identical conditions, the ratio of rates of diffusion of one gas to the other gas, rate of diffusion of first gas to the rate of diffusion of the second gas is equal to d1, or which is equal to root over m2 by m1, or which is equal to root over Vd2 by Vd1, where Vd vapor density is equal to molecular weight by 2, or rather molecular weight is equal to 2 into vapor density. So, this is the relation that exists. Now, so basically the meaning of this is that heavier gas or lighter gas diffuses faster than heavier gas. Obviously, this is simple, as in the general analogy also we know that a heavy object moves slow than a lighter object under identical conditions. Exactly the same thing, a heavy molecule diffuses slow than a small molecule. So, the lighter gases will diffuse faster than heavier gas. This is what the simple thing. And as already we told, rate is equal to volume by temperature, or number of moles by time, volume of gas diffused per unit time, or number of moles of gas diffused per unit time. So, you can also say that R1 by R2 is equal to, when you are writing it as V1 by T1 by V2 by T2 is equal to root over M2 by M1. Now, if two gases, if volumes of gases diffused is same, then R1 by R2 is equal to T2 by T1 is equal to root over M2 by M1. That means, if V1 is equal to V2, then T2 by T1 is equal to root over M2 by M1. And if time of diffusion is same for two gases, then R1 by R2 is equal to V1 by V2, which is equal to root over M2 by M1. Means, for same time, if two gases are allowed to diffuse, then the lighter gas will diffuse by more volume than the volume of the heavier gas. This is what the meaning we can understand. And also here, that rate of diffusion not only depends on the density or molecular weight, it also depends on the pressure at which the gas is present. Because what happens is, as more and more amount of the gas getting diffused, the pressure in the vessel also gets decreases. If the pressure is more, then the rate of diffusion will be more, because the basic definition of the diffusion is what we told is transfer of gas from a high pressure to low pressure. So, as the pressure is getting decreased, obviously the rate of diffusion also decreases. So, rate of diffusion is directly proportional to pressure, or it is also we told that it is decrease in pressure. So, suppose if you are given two gases at two different pressures, then how the relation exists for the rate of diffusion, and how do we ratio of rates of the diffusion of the two gases, how do we measure with respect to the pressure, how does it vary, that now we have to discuss after this. I hope this is now clear, that ratio of rates of diffusions of the two gases at the diffusion of rate of diffusion of one gas, how they are related to the different parameters like density, molecular weight and all of the gases is now we have cleared. And then the effect of pressure, the effect of size of the orifice through which it is diffused, that all also we have to do a discussion. Then here when it comes to the effect of rate of diffusion, is also dependent on pressure at which the gas is present. Because as we told, if the pressure is high, rate of diffusion is proportional to pressure. Or if suppose two gases are at two different pressures, or if same gas is taken at two, if same gas is at two different pressures, that means if you have one gas, if you have a gas here at a P1 pressure, same gas here you have at a pressure P2, this molecular weight is same because it is the same gas, carbon dioxide or carbon dioxide, say let me take, then but the rate of diffusion in the one vessel and rate of diffusion of the other vessel, if you take, the both are not, will not be same. If P1 is not equal to P2, then R1 by R2 is equal to P1 by P2, right. So this is the rate of diffusion. And the second thing is, suppose if you have a long tube, if you have a long tube, if two gases are allowed to pass from the two ends, this is A and B, the two ends of the tube. If this length is say L centimeter, and if two gases, gas 1, gas 2, so suppose like ammonia is introduced from one end, HCl is introduced from the other end, then here there is also a famous question that when ammonia gas and HCl gas is allowed to inside a tube, then at what distance from the ammonia end a white sublimate is formed. Now this ammonia molecular weight is 17, HCl molecular weight is 36.5. So ammonia is lighter than HCl. So in same time the distance at which ammonia moves, travels, will be more than the distance at which HCl travels. So in same time, somewhere over here, suppose a sublimate of ammonium chloride will be formed at what distance? That you can take it as this, if you consider it as x centimeters, then this will be L minus x centimeter, right. Then what we can say is R1 by R2, R ammonia by R HCl will be equal to root over 36.5 by 17 is equal to ammonia, from ammonia side it is x by L minus x. So if the total distance is known, then at what distance this ammonium chloride is formed, that is x, we can determine from this equation, right. And suppose if you don't know one of the gas, suppose this is gas x, then what is the molecular weight of the gas x, that also we can determine. because at what distances the two gases are, or at what distance this white sublimate is formed, that if you know, then suppose if you do not know that this is an HCl gas, then at what distance from this HCl side and at what distance from the ammonia side the sublimate is formed, if you measure practically, then the molecular weight, because this is, if you suppose if you consider it to be an unknown gas, then this molecular weight M2 if you take, and this is ammonia if you take as 17, then the molecular weight of that HCl can be determined, or even any unknown gas also can be determined. So, like this, one first of all, that at what will be the rate of diffusion if two gases are known, that we are not only measure, but with the rates of diffusion what also you can measure is the molecular weight of the unknown gas. Not only that molecular weight of the unknown gas, also what we can determine is the composition of a particular one component in a mixture, also we can determine that. In the next example we see. Now, suppose if it is given that a mixture of oxygen and ozone, that is ozonized oxygen is given, then what is the composition? What is the composition? That means what is the percentage of O2, what is the percentage of O3 in that mixture, if you want to determine. Then by knowing the rate of diffusion, or by determining the rate of diffusion from experiment and comparing it with rate of diffusion of known gas, say oxygen, then rate of diffusion of oxygen by rate of diffusion of mixture will be equal to square root of molecular weight of the mixture by molecular weight of oxygen, that is equal to molecular weight of mixture by 32. So, if these two are known experimentally, this you know it, so you can determine molecular weight of the mixture, and molecular weight of the mixture is equal to x into 32 plus 1 minus x into 48, where x is the fraction of O2 in the mixture. Fraction of O2 in the mixture. So, you can determine, as this is the molecular weight of the mixture which is composed of oxygen and ozone. So, x into 32 plus 1 minus x into 48 is molecular weight of oxygen, molecular weight of ozone. From that what you can determine the fraction of O2 in the mixture. So, using Graham's law, using the concept of diffusion, or as the application of diffusion, what we can determine is the molecular weight of unknown gas or fraction of each gas in a gaseous mixture we can determine. And besides this, there is another very important application of diffusion is about enrichment of isotopes from a mixture, that we see it in the next discussion. So, another important application is enrichment of one isotope of an element in a mixture, or enrichment of one gas in a mixture. How do we do this? This is, suppose you have a mixture of, this is actually done during the World War, where enriched uranium is enriched uranium 238 is required for the nuclear fission. So, from the ore of pitch blende, from the ore of pitch blende, how to enrich 92 or 238 uranium, which is useful for fission. For this, the answer is obtained by the process of diffusion, where this is a mixture of pitch blende is obviously a mixture of 235 uranium and 238 uranium. So, then what it is done is that first this mixture is allowed to react with fluorine. Then what you will get is a mixture of 235 uranium hexafluoride plus 238 uranium hexafluoride. Now, as the molecular weights of the two uranium hexafluorides are different, so obviously the rates of diffusion will also be different. So, here in this R1 by R2 obviously will be different for both the gases. So, as a result, what will happen if you allow the mixture to diffuse out, then you will get one component more. Now, suppose the required enrichment is, suppose initially you started with initial, you have N1 is to N2 and required is N1 prime is to N2 prime, then enrichment factor F is equal to N1 prime by N2 prime by N1 by N2. This is enrichment factor, required enrichment factor. How many times the concentration of one of the component has to be increased, that to determine. Now, what will happen is that rate of first step of diffusion, the enrichment will be equal to, as rate of R1 by R2 is equal to root over M2 by M1, which is the first F1. Now, if you repeated x number of steps, then you will get the required enrichment. So, what happens is, because here R1 by R2 is equal to root over M2 by M1, then F2 will be, in F2 will be root over M2 by M1 into F1, and F3 will be root over M2 by M1 to the power into F2, which is equal to root over M2 by M1 square F1. So, like that, as you keep on doing this, what finally you will get, the required enrichment factor F will be equal to root over M2 by M1 to the power x into F1, right. So, this is the enrichment factor, implies the required enrichment factor F is equal to this is M2 by M1. So, all this is, if you take it into consideration, so this is equal to N1 dash by N2 dash by N1 by N2 into root over M2 by is equal to root over M2 by M1 into to the power x. So, that if you take the logarithms, then this is the required enrichment, that what you know, and this is, you know, you can determine x. So, x, that is number of steps, x you can take it as, now x is equal to log N1 dash by N2 dash by N1 by N2 by this is half log M2 by M1. So, from this the number of steps that are required for the gas to effuse out is what we can determine. By allowing the mixture to diffuse for x number of times, x number of steps from one vessel to the other vessel, one vessel to the other vessel, as you keep on diffusing, then what you will get is at a particular stage, after repeating the process for x number of steps, then the required increase in the composition of 238 uranium is what we can get it, right. So, on repeating we can get it. So, this is another very good application of Graham's law or the concept of diffusion of gases. Besides this concept of diffusion, also we have another term called effusion. Also we have the term called effusion. What is effusion and how this effusion is different from diffusion? In fact, in this application what we discussed is, more precisely we have to say that it is an application of effusion rather than a diffusion, but logically effusion and diffusion both are same, but application wise, concept wise they both are same, but application wise or the process wise or practically they both are different. So, what is effusion is what we say. This is more, as again I am repeating that this is the application of effusion. Now, what is exactly that effusion? Now, we will discuss. What is effusion? As I told, conceptually effusion and diffusion are same, but practically it is different. That effusion is nothing but it is diffusion of a gas through a tiny hole. Diffusion of a gas through a tiny hole. When it comes to applicative part, this is for separation of a lighter gas from a mixture. Separation of lighter isotope from an element. Separation of lighter gas from a mixture. What happens is, if we have a mixture of gases, if you have a mixture, then here a tiny hole you have, from this gas comes out. The gas that comes out first is a lighter gas. So, suppose here you have a mixture of hydrogen, oxygen, nitrogen and all, then hydrogen that comes first, then the oxygen and nitrogen, right. So, this escaping out lighter gas escapes first. This escaping of lighter gas is nothing but effusion. But remember that here, as this being a mixture of gases, the rate of effusion of the lighter gas will be more than the rate of effusion of the heavier gas, and again this effusion also follow Graham's law, right. And now it depends on rate of effusion, depends on the composition or pressure of the gas in the mixture. Suppose if two gases are mixed as N1 is to N2, then rate of effusion of one gas to the other will be equal to N1 by N2 into square root of M2 by M1, or it is equal to P1 by P2 into root over M2 by M1. Using this, what we can determine is the initial composition of the mixture or the composition of the mixture after effusion, both things one what we can determine this N1 and N2. This is what in fact is even that what we have used in the previous example of separating the isotopes 238 or 235 in fact, which is a lighter isotope, right, from the mixture. So, this will gives us suppose here the hydrogen and nitrogen, two gases if you take, and if hydrogen component is more, then anyhow hydrogen being lighter gas will diffuse out fast. But if nitrogen content is more, hydrogen content is less, that means the partial pressure of hydrogen will be very less. If the partial pressure of hydrogen is very less compared to nitrogen or compared to the total pressure, then as diffusion is nothing but from high pressure to low pressure, but partial pressure of hydrogen being less, its diffusion will be less. So, that is what will give us initial composition as well as of course the final composition. If one is known, the others can be determined, and this is the principle. The concept of effusion and its application is even that what we use, as I already told, not only in the separation of lighter gases from the mixture, but also this is the principle that what we use in the spray bottles. In the spray bottles, what we are doing is we will take a liquid in the bottle and a nozzle through it, and when you press it, when you press the spray bottle, what you are doing is you are increasing the pressure. When you are increasing the pressure, the liquid droplets evaporate and they will come out. So, the spray bottle, when you to the spray, when you are increasing the pressure, the gas, the liquid droplets in the vapor phase comes out first, and that is how the spray bottle works out. And also remember another point, that the rate of diffusion, rate of effusion also depends on volume of the orifice. Volume of orifice. It also depends on volume of orifice. If volume of orifice is big, obviously rate of diffusion will be more. If volume of orifice is very small, then rate of diffusion will be slow. It is not only volume of orifice, but the other way, shape of the orifice, whether it is spherical or whether it is cylindrical or whether it is square, depends on that. If the volume of the orifice is changed, automatically the rate of effusion also changes. So, another thing is rate of effusion is also proportional to volume of orifice. That is again very important. So, all the parameters we have to incorporate. Now, how that each one will differ while doing the numerical problems, definitely effect of this orifice, effect of the composition, all this we can understand more clearly when we go for numerical problems. While solving all these cases we will get it. So, this is in totality diffusion, effusion, rate of diffusion or rate of effusion, Graham's law, dependence of rate of diffusion and effusion on various parameters of pressure and nature of the gas, that is the density of the gas and all, and of course the applications. The applications again, to summarize: to detect and to determine the molecular weight of unknown gases, to determine the composition of gases in the mixture, then also to separate out lighter gas from a mixture in separating out, that is the enrichment factor, and also in the mines, in the coal mines, this concept of diffusion is used in the Ansell's alarm. To detect poisonous marsh gas, that is methane, in coal mines, because the rate at which methane gas diffuses out, if methane gas is present in the coal mine, if you take the Ansell's alarm, as the miner enter into the mining, if methane gas is there inside the mine, due to the diffusion of methane, because of the diffusion of methane gas, before we enter deep into the mine, the alarm will detect it and will give the warning, so that poisonous gas is present, whether to enter or not to enter, or at what distance it is present, all this that we can understand. So that is another important application of this concept of diffusion, right. Then more clarity we will get on this while doing the numerical problems.